Hi, welcome to Coding Bootcamp's YouTube channel. Subscribe now and join our live stream session later. See you.
Welcome to this course, Intro to Cloud. My name is Jim Sullivan. I am your instructor. This course is a presentation of Coding Bootcamps. Our first session, Session 1, Cloud Terminologies. Our agenda, overview of cloud technology and cloud technology terminologies. So in a nutshell, the cloud is a term about a global network of servers, hardware, databases, networking infrastructure, all connected by the internet. The cloud is not a physical entity, but it's that vast network of computing resources all around the globe, which again connect to one another using the internet as a medium. And together, they are meant to operate in a single ecosystem. So some cloud terminology. So artificial intelligence, AI, is available on the cloud. And what AI is, it's certainly applications, data, and hardware, very fast hardware. It's meant to use data to actually make decisions. So it can make decisions or recommend decisions in order for better business outcomes. Business analytics tools, also analyzing data, looking for trends that may not be necessarily obvious. This allows for better direction of resources within the business and also just in general, better business decisions. Cloud bursting, cloud computing, these are all ways of scaling up, essentially almost like renting computing resources when I need them and then stop paying for them when I don't. Cloud computing types, there are types such as infrastructure as a service, which gives us our hardware and our networking that is, again, almost like a rental model. When I need to scale up, I can pay either by the hour or the month for that additional infrastructure. And then there's platform as a service, which gives us a database and other types of almost middleware for additional computing power when needed. And then there's software as a service, which are software applications similar to Gmail or Yahoo Mail or something like QuickBooks, where I don't have to run the application on my own computer or my own infrastructure. I just pay almost like a subscription for those vendors to actually host that application for me. A cloud service provider, somebody like an Amazon or a Microsoft Azure who actually has these data centers and makes this cloud computing infrastructure available to the public and to businesses. And cloud storage is, just like it said, it's part of infrastructure as a service. You're able to use additional storage or scale up storage and have those cloud computers, which are offsite in remote data centers, store data for, again, individuals or businesses. Computing grids are really set up, are almost localized networks of data centers that operate, that try to make the cloud and the performance as efficient as possible. Data sharding, DevOps, these are all covered. DevOps is both a methodology, but it's also a way of hosting data. Elastic computing, like the term, like it looks like, elastic computing gives you the ability to stretch up or add resources as needed, and then when you don't need it, it can return back to the size that you had. Hybrid cloud, that is covered in the next session, but that is a way of actually taking cloud servers and making them part of the business network by using a virtual private network. Infrastructure as a service is covered in the next session, and we already introduced this. This is storage and networking and hardware that is available to me in the cloud by cloud providers. And we did talk about machine learning, that artificial intelligence, again, learning tracking the outcome of certain situations, and then making better business decisions. It's all done through algorithms. So the computer programs do return a decision. The outcome and the results are noted. If desirable, the computer will tend to pick those decisions more. If not, will make other decisions. So the algorithms actually learn based on outcomes. And middleware are almost runtime type of environments, things like web servers and other Java runtimes. They actually allow for calculations. They actually allow for web pages to be built and for mobile applications to be built. So it's that middleware, that the middleware is not something that the user directly interacts with, but it provides that layer of processing that will return data back to the user and take the requests from the user. NoSQL is a certain type of a database. These databases are very, very efficient, as opposed to a relational database, which uses tables, and there has to be a specific a structure query language used to get data out of these databases. NoSQL has a place in being very, very fast and efficient. Again, we talked about platform as a service, covered in the next section. Private cloud, we'll talk about this, but private cloud is an on-site data center. A public cloud is somebody else's data center that a business or an individual enters in a business agreement with, and they will either host or somehow rent or make available computing resources when needed. Software as a service we've already introduced, and that's covered in the next session. Serverless computing is actually quite interesting. That is where only when an application is needed, a server actually comes on the fly. It almost sleeps while it's not being used. And it's only that virtual hardware, that cloud hardware, only comes on when needed. So that is a way to keep costs down. Although at times it can be slow because there's that time period when the serverless computer and the application need time to come online. A virtual machine is a way of using hardware, or as a way for computers or for special software allowing computer images to actually share hardware. And virtualization allows for computers to use certain connectors and certain objects to connect to the hardware exactly the same as a physical machine would, allowing the hardware to be available to many computers at once. So please consult your training materials for more discussion on cloud terminologies. And as a recap, we had our overview of cloud technology, and we had we discussed cloud technology terminologies. Our next session is Introduction to Cloud Computing. Thank you again for watching this video, and again, this was a presentation of Coding Bootcamps. Welcome back to this course, Introduction to Cloud. This course is a presentation of Coding Bootcamps. This is session 2, Cloud Computing. Just to recap, this is what we have learned so far: an overview of cloud technology and cloud technology terminologies. Our agenda today: overview of cloud computing, the different types of varieties of cloud computing, public, private, or hybrid, types of cloud services, so software as a service, infrastructure as a service, or platform as a service, and uses of cloud computing. So in general, cloud computing is the delivery of computing services, including hardware and servers, storage, database, networking, software, analytics, and intelligence, using the internet as a medium. So to offer faster invocation, flexible resources, and economies of scale. Often, it's a rental model. So when you need additional computing power, you can contract with a cloud provider, and they can actually deliver to you the additional computer resources you need for the time that you need. And then when it's no longer needed, those computer resources are then powered down and you are no longer charged for them. Different varieties of cloud computing. So there is public clouds, which is something like an Amazon or something like an Azure or the IBM cloud. That's where a business is offering computing services to another business or an individual, again, over the internet, using the internet as a medium. There are private clouds and also virtual private clouds. So a private cloud, pure private cloud, would be a data center which is owned by the firm itself, which is under the control of the firm itself. And then they are able to create cloud images or offer cloud services to the business. And then there's hybrid cloud, where the firm is actually using some local or some private cloud products and also using the services of a public cloud. And then there is a virtual private cloud where a public cloud provides computing services. However, the computing services being offered by the public cloud provider put a virtual private network or a VPN on the computing software, so it actually becomes part of the customer's network. So again, types of cloud services: SaaS or software as a service, infrastructure as a service, and platform as a service. So we could see here software as a service. Those are hosted applications or apps. So Gmail is a very good example of software as a service, or QuickBooks. Then there's platform as a service. Those are database management and business analytics, and also operating systems that are available for customers to use with their own data and their own applications. They just don't need to provide the database. They use the cloud provider's database. They don't need to provide the operating system. The customer uses the cloud provider's operating system. And then infrastructure as a service includes storage and storage devices, servers and hardware, networking, firewalls and security, and data center physical plants and buildings. So the uses of cloud computing: to create cloud native applications, so to build applications and run them on the cloud and take advantage of the cloud's ability to scale up when needed. Test and build applications. So quite often firms need to test applications, but they don't want to be maintaining all the testing hardware. So they will have a cloud provider deliver the testing hardware, which will be identical to the production hardware to get a better test. And also the applications can also be built within that cloud environment as well. Storage and backup and recovery. So this would be off-site storage of data. Analyze data, so take advantage of the incredible computing power that many of these data centers have in order to analyze data and search for trends. Again, take advantage of the expanded resources of a cloud provider and stream audio and video. Embed intelligence, so any applications that are able to process intelligence, and also deliver software services on demand. So whether the firm needs certain software, such as Salesforce type of software, or even a accounting type of applications, or HR type of applications, it can be delivered to the firm as needed. The firm doesn't have to worry about all the overhead of hosting those software applications. And also, firms can make their software products available to their customers through the cloud. So more on cloud computing. So for more discussion on cloud computing and its business use cases, consult your learning materials. Again, a recap, we had our overview of cloud computing. We talked about
Thanks for watching. Feel free to add your questions as comments down below.
the types of cloud computing, public clouds, private clouds, and hybrid clouds, types of cloud computing services, software as a service, infrastructure as a service, platform as a service, and the uses of cloud computing. Our next session is Introduction to DevOps. This is a great topic. Again, thank you for watching this video, and this video has been a presentation of Coding Bootcamps. Welcome back to this course, Intro to Cloud. This course is a presentation of Coding Bootcamps. This is session 3, Intro to DevOps. Just to recap what we have learned so far, we had our overview of cloud computing. We explored the varieties of cloud computing, including public, private, and/or hybrid. And we explored the types of cloud computing services, such as software as a service, infrastructure as a service, platform as a service. The agenda for this session, we're going to look at what is DevOps, DevOps adoption, DevOps tools, and what is CI/CD, or continuous integration and continuous deployment. So our introduction. So the term DevOps is actually a combination of development and operations. So sometimes these groups have conflicting goals. So development teams like to continuously improve, add more features, fix defects. Product managers, the same thing, want to continuously improve, add more features. Operations teams prefer to stabilize, to keep the product running once it's stable, keep it available, and deployments, changes, updates tend to cause issues with that stability. So the idea here is to make that bridge between development and operations. So DevOps is a set of practices that includes automation of processes between the development and the IT teams. So IT teams can automate their build, test, and release processes faster and more reliably, and also with fewer errors, and also to ensure that builds run successfully and often, and tests run often, and all products are tested, and there are ways to automate testing using testing scripts. So DevOps looks again to create that unity between development teams and operations teams. It is an agile methodology that involves continuous delivery for continuous feedback from customer representatives of the customer to do testing. It also involves automation, and is there to help development and operations teams be more efficient, innovate faster, and deliver higher value to the business and the customers. So the promised benefits include an increased trust, faster or sooner delivery of software releases to solve critical issues quickly. So there could be problems, defects, or there could be features that absolutely have to get released, or there could be things like security type of fixes that need to get released, and also better managed unplanned work. So the software development process can't work efficiently without the right tools. And software development is still, even today with the right tools, is still a very complex activity. So in the case of DevOps, teams can benefit with the right set of tools and the right process. It's always the right process that's important. The tools can be configured to support the right process, but the tools do help in sharing information, progress, process automation, reduction of deployment time, and reduction of human error, and in continuous deployment in order to get continuous feedback on whatever updates were made to the software products or the software devices. So we can see here again, development teams like to plan, like to create, package, verify, well as operation teams. They like to monitor, they like to stabilize. Both teams share in releases. However, anything new to the operations environment can be a risk to stability. So teams need to work together to continuously improve, to continuously create, and continuously release, while still continuously monitoring and continuously stabilizing. So some tools used in DevOps: Ansible, which is an automation framework; Docker, which gives a virtual runtime environment that is quick and easy to deploy to. Kubernetes is also a runtime environment that is quick and easy to deploy to, and also it has certain features which allow for several different clusters of the application to run to handle loads and also for backup situations. Chef and Puppet are automation frameworks for automating release. We have a set of tools here, a set of tools for process. So we have EC2, Docker, all runtime type of environments. Git is a repository that allows for teams to actually check in their files, their code files, whether it's for a software product or for a device that's running software. Jenkins is another automation framework that allows for commits to be automated, builds to be automated, and deployments to be automated. And AWS also has a suite of tools, including Code Commit, Code Build, Code Deploy, and Code Pipeline. Again, just like these tools sound, they automate and they help teams with automation of committing, building, deploying to a runtime environment like EC2, and Code Pipeline for continuous continuous delivery pipeline. So again, we can see here on our development side, we plan, we code, we build, we test, and this is what development teams do: continuously improve and continuously fix any types of software products, software that runs on devices. We can see here Git is a tool, Maven is a tool, Gradle, JUnit. JUnit is an automated scripted testing framework. For integration, there's Jenkins and Bamboo to help get this code from the development environment over to some kind of staging environment, and then from that staging environment integrate with deployment to some kind of an environment that is very, very similar to production. And the tools that can help us with deployment are Puppet, Docker, and Chef. And once deployed, tools to help us with operating and monitoring are tools like Splunk. This is just some of the organizations using DevOps. DevOps is really a suite of best practices. We can see these firms, but many, many, many more are using DevOps. It's a very successful methodology. And we can see here the DevOps market size by application is growing, and it's looking to grow out into the mid-2020s here. It's looking to grow substantially by the mid-2020s. CI/CD, again, stands for continuous integration and continuous delivery or continuous deployment. And you can think of this process as similar to the software development lifecycle. This is a methodology where applications or devices and applications are delivered to customers by using automation and steps in automation, or these could be representatives of the customer. And the main concepts attributed to continuous integration and continuous deployment are automation of that continuous delivery pipeline. So if we integrate continuously, that process is going to become less difficult. We'll be able to actually smoke test integration and smoke out problems sooner. Continuous delivery will allow us to validate that the product we built is running correctly in the runtime environment, and then continuous deployment allows us to deploy to staging environments, pre-production environments, and also the production environments. CI/CD is a solution to many problems, and it's a way of integrating new features and new code, and that can allow development teams and operations teams to operate in an environment where there is actually less friction and more satisfaction between the teams and the customers. So we can see here the flow. There is a lot of times the products begin as source code, and there is a commit. This process can certainly be automated, and it often is. We already talked about Jenkins as one of these tools. And then within the continuous integration pipeline, builds can be run, which take it from source code to actually machine code. JUnit helps us run automated tests, and this is good just in and of itself because this is showing that when code is checked in, it is tested, and that's always important. Also integration tests. Again, this is all looked to be automated as much as possible. However, there can be times when manual testing is also run. And then to get to the continuously delivery pipeline, we take the product that's running now, that has been tested automatically, and it can get reviewed in some kind of a staging environment. And if everything is running in a satisfactory way, if the customer or representative of the customer is happy with it, then deployment to production can happen and release announcements can be made. And again, all of this can be automated and should be automated. Great practitioners of DevOps automate all of these steps and more in many different ways. So again, Jenkins is a great automation framework. It can be the ultimate continuous integration tool, and it does have a lot of importance when it comes to the CI/CD pipeline. So our task is to automate the entire process from the time the development team gives us the code and commits it to the repository. And it's from the time that we eventually deploy to production. So our task is to automate the pipeline as much as possible in order to make the entire software development lifecycle on DevOps more automated. More automated is better. It reduces error, it increases reliability, increases the time to market, and increases quality. So for this, we need automation tools. And again, we can see here Jenkins and Git together. So Git is a repository, and Jenkins again is that automation framework. So we could see developers are working, committing their code to the repository, and then from the repository out to Jenkins. And then Jenkins looks to automatically commit and then run that build where it goes from source code to an executable file for that operating system. Automating testing, so calling those scripted tests and looking for the correct results. Staging to an environment where the product can be viewed by representatives of the customers or customers themselves. And then deployment to either some kind of pre-production environment, QA environment, where again, more evaluation can take place, and then ultimately to our production environment. So other DevOps tools, we cover tools like these, like Docker and Kubernetes in our next sessions, but these are fantastic DevOps tools, very popular, and they are incredible products that add a lot of value. Just to recap what we covered, so what is DevOps, DevOps adoption, DevOps tools, and what is continuous integration and continuous deployment. So for more on DevOps, please consult your learning materials. And our next section is Introduction to Docker. Some live DevOps classes. There are live training classes available for mastering Docker and containers in cloud environments, training classes on mastering Kubernetes in a cloud environment. and complete training on mastering DevOps and all of its tools. Thank you for watching this video on DevOps, and this has been a presentation of Coding Bootcamps.
If you have enjoyed watching this video, please subscribe to our YouTube channel. Thank you.
Welcome back to this course, Introduction to Cloud. This is a presentation of Coding Bootcamps. This is session 4, Introduction to Docker. What we've learned so far. So we had our overview of cloud computing, the varieties of cloud computing and types of services, including public varieties, private, hybrid, software as a service, infrastructure as a service, and platform as a service. And we discussed DevOps. So the IT landscape is changing. Application development needs to be done faster with more features, more runtime environments, such as mobile. DevOps needs to be used to automate that delivery in order to respond to the demands of the marketplace. And cloud is changing the landscape as well. It's allowing even small firms to have the access to large computing infrastructure. Movement to the cloud. So it's believed maybe around 80% of the movement to the cloud is complete. So, and this includes migrating workloads to the cloud, portability across environments, so the cloud enables that, and avoidance of cloud vendor lock-in, which could be an issue. Once all of your data and all of your infrastructure, your virtual infrastructure is with one cloud vendor, it can be difficult, it can be a task, it's not impossible to migrate away to a different cloud provider. So make sure you have the proper agreements in place which will at least smooth the process of migrating from one cloud services provider to another. We can see here applications are transforming. So at one time there was the monolith, so the large hardware, very slow to change, big servers, all applications ran a lot of times on premises at the firm. Whereas today there are smaller microservices which are connected quite often over the internet. They are often loosely coupled services, rapidly updated, very reusable, and small services, and also services that can act as backups for one another. So it is almost like the monolith, but just operating in pieces instead of a one monolithic structure. And application monitorization. So there was application code, and there was minor code changes required a full compile, often a retest, any kind of regression testing. Applications became a single point of failure, and applications were difficult to scale up because if all of the computing infrastructure was within the firm actually had to budget all of that physical hardware. So if we break into microservices, each microservice can specialize in its section of the application. And 12 factor apps make the apps more independent, more scalable, more stateless, and highly available by design. So we can see here again continuous integration and delivery. So there is a version control quite often provided by Git or a similar tool. The developer checks all of the code into the version control repository, and then testing can happen. So Jenkins here, we can see Jenkins can actually build the source code that the developer developed. We can see it here, source code comes in and executable code comes out. And even some QA can happen during this time. So obviously If the code builds, that's a test right there, because quite often builds can fail. And automated tests can run during this time. Automated tests such as JUnit testing. And then the environment through automation can actually stage to pre-production environments and eventually to production environments. And all this time, we can see the developer role here in the development section. A QA analyst or quality engineer operating the tools and the automation during the test phase, and then a system admin making sure that the product is stabilized, it's monitored, and it's secure. So this has come up for a long time. There's been a tug of war and often conflicting ends for developers and operations. Again, developers want to continuously improve and fix applications. Product managers, the same thing. They want to increase functionality, add capability. IT operations, they like to stabilize. So they want to, once they have something running and secure, a lot of changes, a lot of updates could disrupt that stability and that security. So organizations must deal with that diverse technology. So bare metal, obviously that's hardware right out of the box, on premises, adding in operating systems and some kind of traditional security. Plus that now there is the ability for virtualization. So having several different computers share the same hardware and make the hardware more efficient, the same disk, the same memory. Cloud, where typically a cloud provider, an off-site data center, is able to manage my computing infrastructure for me. And when I need more, I can simply just request more. When I don't need additional computing resources, those computing resources go away. Windows, again, we have our different operating systems, not only Windows but Linux, and these microservices which allow for specialization of running certain sections of the application or even devices. And when it comes to this, only the microservices that need updating receive the updating. So again, the diverse organizations, again, developers, they need the freedom to create and deploy fast, define packages. IT operations, again, very important to secure, very important to stabilize, to measure, to make sure the customer is getting the value that they are expecting. And here is the myth of bimodal IT. There is the microservices world, usually associated with cloud and new infrastructure. So we're either here or we're in the traditional part, the traditional quadrant, the old infrastructure. So you're almost never in both the traditional and the microservices. You're in one or the other. Enabling the journey again, or the microservices, the agility, and our traditional applications. So this is our journey from the old infrastructure to the cloud and the new infrastructure. So let's look at Docker and containers. Let's look at the overview. So here, a little bit of history. So Solaris, in around 2004, creates Solaris containers, and Zone Technologies are introduced. So containers can be thought of as just the dependence, just the application and the dependencies running on top of a common operating environment. Then in around 2008, Linux containers were introduced. And then Docker is started as an internal project. And then Docker is then released in 2013 as an open source product. Docker continues to introduce the first commercial product, now called Docker Enterprise. And the difference really between the community edition of Docker and the Docker Enterprise is support. So if Docker Enterprise is desired, the users would just pay for support of the Docker tool. So today, there are more than 3,000 open source communities, more than 43,000 contributors to Docker, and there have been more than 12,000 forks of the technology, meaning that different development paths have been created for Docker. And there has really been incredible adoption in just 4 years. So we can see here that the Docker hosts 14 million, 900,000 Docker applications. The growth here in Docker job listings has gone up by 77,000%. Images have grown, and also the number of contributors have grown in just a relative short amount of time. A little bit of a history lesson. So this was the physical server, the physical hardware. There was actually physical hardware that was built. So we can see the physical layer here. The operating system is a special program that's installed that runs on this hardware. It's built to run on this hardware. And then there are applications that run on top of the operating system, and the operating system is in charge of managing the resources for this application, including memory, disk, video, and other resources. But there are limitations when it comes to managing applications in a physical environment. Number one, you have to have enough physical environments for the demands of your application. So scaling was hard. Slow deployment times, because a lot of times the configurations of the operating systems could drift, could change slightly. Updates could happen at different times. Environments that were thought to be absolutely identical turned out not to be identical. Wasted resources, huge costs in managing all of these physical operating systems, including electricity and backup. Difficult to scale, so it required a large budget to scale. Difficult to migrate, as these systems need to be upgraded. It takes time and effort. And yes, vendor lock-in as well. So quite often it limited the options of the firm to go with physical software and hardware. And a little bit of a lesson here in virtualization. So virtualization, this is a brief description of virtualization. So there is physical hardware and a host operating system and a special program or a special application called a hypervisor. And what a hypervisor is, it's a tool, a software tool that allows you to control guest operating systems. So different guest computers run separately on the hypervisor with their own IP address and their own host IDs and their own instance of the operating system. So they share a common operating system, and they share a common physical infrastructure. So one server can run multiple applications, and each application runs on its own virtual machine. And these virtual machines are using certain software objects to map back to the host operating system and the physical server in order to function like independent computers. Well, the benefits of virtual machines are better resource pooling, certainly better use of resources. So one physical machine can be divided into multiple virtual machines, allowing the resources to be used more efficiently. Certainly easier to scale. If we need more machines, we just simply go into the hypervisor and create more virtual machines. And VMs in the cloud, so rapid elasticity, meaning that I can stretch my environment. If I need 5 more, I can easily order five more virtual machines. If I need 10 more, I can easily order 10 more. And then I can also scale down as needed. And it is a pay-as-you-go model, typically some kind of a subscription model. So even smaller firms can have access to the resources of the biggest enterprises. And some of the limitations of VM. Each VM still requires capacity allocation, so it still requires access to the hardware. It still requires physical storage. It still requires RAM. The virtual machines share all this, and there is still an entire guest operating system that needs to run on this infrastructure. The more virtual machines you run, the more resources you need, and guest OS could mean wasted resources. And application portability, this is big here. Application portability is not guaranteed. Just because you have a copy of one application and a copy of a virtual machine does not mean if you zip it up and then unzip it and run it that the application is going to run the same. the outer services, the outer physical layers may not allow that. The networking may not allow that. So one response to that, one response to those limitations.
Thanks for watching. Please like and share this video.
Of the VM was the container. So the idea with the container is the application and the dependencies are all stored in the container. So the container is not a full virtual machine, but it does allow for virtualization of the application and its dependencies. So you can see here Java, the operating system, and a runtime environment such as Tomcat. Here we can see a database, an operating system just as an application such as .NET here, and also we can see here Alpine, which is a tool, and static binary. All in these containers, they all share this common kernel. So these containers represent microservices that are much more portable between the Docker kernels. So here, standardized packaging for the software dependencies. So all of the applications and the dependencies are standardized. Obviously, applications are isolated from one another. They share a common kernel. So they don't share dependencies. And they have, if we look here, we can see an operating system here. We can see things like .NET and Java. So that's not being shared, but the kernel is being shared and works with major Linux and Windows servers. So if we compare containers with VMs, we can see here our container just has the application, and the libraries and the binaries are just here within the containers. Then they run on top of Docker. It's Docker that runs on the host infrastructure and the host OS. So we can see here these containers are quite portable, provided that they are using a compatible Docker environment, and that Docker environment is running on a compatible host OS and infrastructure. So containers are an app level construction, whereas here you see VMs are infrastructure level constructs that turn one machine into many servers. So we can see here there are actually 3 VMs here. They all have their own version of the operating system. They all have their own version of the binaries and libraries, or the dependencies, and they all have their applications running. There's a common hypervisor and a common hardware that the hypervisor is running on. So the containers actually are the microservices. It's very, very limited to just what's needed. Therefore, they're much more robust, much more portable. And the promise of containerization is those containers will run anywhere on any runtime environment, including, in this case, it's Docker. So we can see here containers and VMs together. So we can see here a dev environment, a Docker hosted environment, where we have these 3 applications packaged in the containers with just their dependencies running on the Docker runtime, and Docker is running again on its host OS and infrastructure. Where in the prod environment, Docker is also being hosted with a guest OS. So we can see here the 3 guest OS that are running on top of the hypervisor and the physical hardware. And we can see here that these guest OS have their own Docker runtimes, and these Docker runtimes are supporting apps A and B and their dependencies. App C, which may need the resources of its own Docker runtime and its own guest OS. And then we can see here how this could be a non-containered application that just really needs the application, the dependencies, and its own guest OS. So this is a very, very flexible solution. So some key benefits of Docker containers. So speed, certainly. It's less maintenance because these are all microservices. So no OS to boot, applications online in seconds, highly, highly portable. Again, Docker containers are not full virtual machines. They're just the application and its dependencies. So provided that the Docker runtime is compatible, the containers can run on top of that Docker runtime. Highly efficient as well, less operating system overhead, and improved VM density, meaning that I can use both containers and VMs together, so I can have a more efficient infrastructure with virtual machines and density. I can run more virtual environments because I'm just using containers and not full guest operating systems. So just a little bit of a recap. We had our introduction to Docker and the Docker environment. Our next session is Introduction to Kubernetes. Please follow up with some live classes, including training classes for mastering Docker and containers and cloud deployment, live training classes for mastering Kubernetes, containers, and cloud native, and complete live training for mastering DevOps and all of its tools. Thank you for watching this video on Docker, and this has been a presentation of Coding Boot Camps. Welcome back to this course, Introduction to Cloud, a presentation of Coding Boot Camps. This is session 5, Kubernetes. In this session, for our introduction, we're going to talk about what Kubernetes is and what it does. And we're going to talk about the architecture, so master components or master nodes, worker nodes, and additional services. So for our introduction here, first we'll do our recap. We had our overview of cloud computing, our varieties and services of cloud computing, including public, private, hybrid clouds, and our services are software as a service, infrastructure as a service, platform as a service. We discussed DevOps and Docker. So Kubernetes, or sometimes abbreviated as K8s, was a product that spun out of Google. Ultimately, it became an open source next-gen container-based scheduler designed to lessen the burden from managing such products, internal products as Borg and Omega. Kubernetes was designed from the ground up as a loosely coupled, containerized organization, running a collection of components centered around deploying, maintaining, and scaling applications. So it is a runtime environment. What does Kubernetes do? Well, Kubernetes is the Linux kernel of distributed systems that abstracts away the underlying hardware of the node and provides a uniform interface for applications to be both deployed and consumed from a shared pool of resources. So a little bit about the Kubernetes architecture. So there are master nodes, and they act as the primary control plane, and that is quite often a term in Kubernetes. So master nodes are the control plane for the Kubernetes product. Master nodes are responsible at a minimum for running the API server, scheduler, and the cluster controller. Commonly, they also manage the cluster state, cloud provider specific components, and other clustered essential services. Worker nodes of the Kubernetes cluster run and agents that manage the node itself, and they are tasked with executing workloads as designated by the master node. So we can see here a typical architecture. So we have our master node here. We have our user using a kubectl product that's connecting to the API server. We have a cloud server API. We have something called the etcd. We see our containerized runtime and our kubelets. So this is the master node, and it is connecting with the worker nodes. And in the worker nodes here, we have, again, our kubelet, our container runtimes, our kube proxy, and our pods. So just like these are named after pods of dolphins or pods of whales. The pods are where our applications are running. So we can see here, again, these two nodes are identical. They are load balanced with respect to the users. So some of the master components, run the API server, the etcd, or sometimes called etcd, the kube controller manager, the cloud controller manager, and the kube scheduler. So if we take a look here, we can see these services, the system services, the kubelet, and the container runtime, all interacting with the etcd and the API supervisor, or API server. That is where the user is actually interfacing with the master node. And we can see here additional services such as the kube proxy, the scheduler, cloud API managers here, kube controllers. The Kube API server provides a straightforward facing REST interface into the control plane. So all clients, including nodes and users and applications, interact with Kubernetes strictly through the API server. It is the true core of Kubernetes, acting as the gatekeeper to the cluster by handling authentication, authorization, request validation, mutation, and admission control, in addition to being the front end to the back end data store. So the Kube server, again, provides a lot of the access to the product. The etcd acts as a cluster data store, so saving the state of certain saving the date of the data store, providing a strong, consistent, and highly available key value store for a persistent cluster state. And again, it saves the state. It also saves the state of the cluster. The Kube controller manager is primarily a process that manages all core components and control loops. It monitors the state of the cluster via the API server and steers the cluster toward the desired state. So when it talks about a cluster here, if originally we configure three clustered state and one of those clusters goes offline, the state will be brought back to the desired state again, which is 3. So the API server will then spin up another, or create another cluster to bring it back to the desired state. Cloud Controller Manager is that process that provides the cloud provider with specific knowledge and integration capabilities into the core control loop of Kubernetes, and controls include the node, the root, the service, and additional controller to handle persistent volume labels. The Kube Scheduler is a verbose, policy-rich engine that evaluates the workload and attempts to place it on a matching resource. So it is looking for a runtime that can actually manage the demands of the application and the demands of the users. The requirements can include such things as hardware requirements, affinity, and other custom resources. And node components. So the kubelet, the kube proxy, and the container runtime engine are the components of our worker nodes. So we could see here our container, again, the container runtime. We see the pods in the containers, our kube proxy, and our system services here. Again, these kube proxies and the kubelet are connecting back to the master node. The kubelet acts as a node agent responsible for managing our pod lifecycle on the host. Kubernetes understands YAML container manifests. So YAML is a specific markup language, and it can read from several resources such as file path, endpoints, etcd watch acting, and HTTP server mode, accepting container manifests over a simple API. The kube proxy manages the network rules on each node and performs connections for load balancing for Kubernetes clusters. So if there, again, is a state which requires several images or several pods to be running an application, it will be creating and make sure that that desired state of 3 or 4, whatever that desired state, is maintained. And available proxy modes, user space, IP tables, and IPVS. our container runtime. So with respect to Kubernetes, a container runtime is a CRI, again, container runtime interface. Quite often it can be Docker. So there are others, we can see them here.
Thanks for watching. Feel free to add your questions as comments down below.
And there are several containers that are compatible with Kubernetes. So Docker is one of them, and it probably is the most popular. There's CRIO, RKT, and we see here Kata and Vertlet. Additional services are kubedns, so that provides cluster-wide DNS services. So a lot of times there'll be DNS mapping and local host use within Kubernetes, so it's very important to track the DNS. The Heapster is a metrics controller for the Kubernetes cluster used by some resources such as the horizontal pod autoscaler. And quite often this is required for the dashboard metrics. And there also is a Kube dashboard, which is a web-based UI which displays gadgets and little viewlets with metrics on the Kubernetes environment. So in summary, we had our introduction and we discussed Kubernetes, what it is and what it does. And we discussed the architecture. We talked about the master node, the worker nodes, and the additional services. For live classes on Docker and Kubernetes, please consult your learning materials, and also live classes for mastering DevOps. Again, please consult your learning materials. All of these are great classes. And thank you for watching this video. This is our concluding video on the introduction to cloud. This has been a presentation of Coding Bootcamps.